Welcome to The Explainer, where today we're going under the hood of one of the fastest blockchains in the world. We're going to figure out what it actually takes to run a Solana validator. When you think of Solana, you probably think of one thing, just raw, unbelievable speed and transaction throughput. And look, this isn't just a number on a marketing slide. Under real-world network load, researchers have actually clocked it sustaining an average of over 4,500 transactions every single second. So how in the world does it pull this off? Today, we're connecting that revolutionary theory to the real-world hardware and the crucial security decisions that operators have to make day in and day out. All right, it all starts with Solana's foundational innovation, a really cool concept called proof of history. So what exactly is proof of history? Now, it's super important to get this right. This is not a consensus mechanism like proof of work or proof of stake. A much better way to think about it is as a cryptographic clock, a way for the whole network to agree on the order of events without constantly having to talk to each other. At its core, it's actually kind of elegant. A secure hash function just runs in a continuous loop. The output of one calculation becomes the input for the very next one, and this creates a sequential, provably unforgeable record of time passing. Now, this is where the transactions come in. They aren't just added to some list. Their data is literally woven into this ongoing chain of hashes, and that permanently locks them into a specific verifiable moment in history. And here is the real genius of the system. While that clock has to be generated sequentially, one tick after another, verifying that the clock is correct can be done in parallel. A validator can throw thousands of cores at it, checking different pieces of the chain all at once, which makes verification exponentially faster than generation. So let's tie this all together. By creating this verifiable clock that everyone agrees on without talking, Solana's execution environment can just go. It can process huge batches of transactions in parallel without waiting around for consensus on the ordering. That is the secret sauce to its speed. Okay, creating a clock that fast is one thing, but you need a seriously high-performance machine to actually run it. So let's get down to brass tacks. What does the hardware reality look like? As you can see, this is not your average gaming PC. We're talking about serious server-grade hardware with a heavy focus on fast CPU clock speeds, massive amounts of RAM, and multiple super durable SSDs just to handle the insane data flow. And listen, the official guidance here is pretty blunt. For top stability and performance, you need to be running on dedicated bare metal servers. Virtualization layers, whether from cloud platforms or Docker containers, they just add too much performance overhead to be reliable. All right, so you've built the machine to spec, but is the official recommendation really enough? Well, some researchers decided to find out by absolutely hammering the two most critical components, RAM and the program cache. And wow, the results were eye-opening. The data shows that while a machine with 256 gigabytes of RAM can technically run, it spends a shocking amount of time completely idle, processing 0 transactions as it just struggles to keep up with the network state. I mean, this chart just lays it all out, doesn't it? You can literally see the instability growing as the RAM goes down. That validator with 256 gigs of RAM was effectively stalled, doing nothing, for over a third of the entire 12-hour test. So the researchers' conclusion? It's pretty stark. They say 512 gigabytes of RAM is the real baseline for stable performance. That common 256 gig setup that many people run is, in their words, dangerously close to instability. It's living on the edge. Next, they took a look at the program cache. You can think of this as the validator's short-term memory for smart contracts. And what they found was the default size was just way too small, causing the validator to constantly forget programs and have to reload them from the slow disk, which just kills performance. But here's the kicker. The fix was ridiculously simple. Just by increasing the cache size in the configuration file, operators can slash the time spent on these cache operations by nearly 90%. That is a massive performance gain with absolutely 0 extra hardware cost. So now we have a powerful, optimized machine. The final, and you could argue most crucial step, is to secure it. A validator is a valuable asset, which makes it a prime target for attackers. First and foremost, and this is completely non-negotiable, never ever run the validator process as the root or administrator user. If there's an exploit in the software, that's it. You've given an attacker total, unrestricted control of your entire system. Equally important is your withdrawer key pair. This thing controls your funds and your vote account. It needs to be generated on a trusted, offline computer and stored securely somewhere else, never on the validator machine itself. When it comes to remote access, you have to disable password-based logins entirely. Use only cryptographic SSH keys. They are far, far more secure against the constant barrage of automated brute force attacks happening on the internet. So, beyond those hard rules, a strong security baseline really comes down to 3 key practices. Keep your system constantly updated, use a firewall to limit your attack surface, and install tools like Fail to Ban to automatically block suspicious login attempts. So the takeaway here is pretty clear. Solana's incredible speed is a direct result of proof of history. But that performance comes at a cost. It needs expensive hardware and deep operational expertise. And this raises a really crucial lingering question for the whole ecosystem. What's the right balance between raw performance and the kind of accessibility that's so vital for true decentralization?